Good day, everyone. I'm Sunny Zacarias from the University of Southeastern Philippines. Today, I will present our study titled Securing LoRaWAN IoT Data Streams in Smart Banana Plantations using a Hyperledger Fabric-based prototype. This study is part of the 8th IEEE Symposium on Computer and Informatics 2026 in Kuala Lumpur, Malaysia. The study begins with a simple but important question. As farms become more dependent on sensor data, how can we make sure that the data remains trustworthy? To answer that, let me first begin with the background of the study. Smart banana plantations are becoming more dependent on IoT sensor data to monitor field conditions and support daily farm decisions. But in large plantation areas, collecting data is not always simple. Sensor readings need to travel across long distances, often with limited connectivity and low power availability. This is where LoRaWAN becomes useful. It allows sensor data to move across wide farm areas using long-range and low-power communication. However, the challenge does not end once the data is collected. After sensor records are stored, they must still remain reliable, traceable, and protected from possible changes. This leads to the main gap of the study. Previous studies have already explored IoT, LoRaWAN, blockchain, and traceability systems in agriculture and supply chain settings. However, many of these studies looked at these technologies separately. Some focused on data transmission, others on visualization, access control, or supply chain traceability. What remains limited is a plantation-specific system that checks whether stored banana sensor data remains unchanged after collection. This study brings these technologies together into one integrated prototype for smart banana plantations. From this gap, the study set out a clear objective. The objective is to determine whether banana plantation sensor records can be transmitted, stored, hashed, and verified securely. Sensor data may reach the system, but the key question is, can it still be trustworthy after storage? This study responds to that question by evaluating a Hyperledger Fabric-based prototype. The prototype connects LoRaWAN, ChirpStack, PostgreSQL, and Hyperledger Fabric into one data verification pipeline. In simple terms, the study follows the journey of the sensor data, from field sensing to transmission to storage to hashing and finally to blockchain verification. The goal is to check whether banana plantation records can remain reliable, traceable, and tamper-evident. To test this, the prototype was evaluated through data flow validation, reliability testing, hash verification, tamper detection, and transaction performance testing. With that objective in mind, let me now show you how the prototype was implemented. This slide shows the full journey of the sensor data in the prototype. The process begins in the field, where the LoRaWAN sensor collects the environmental readings and sends them to the gateway. From there, ChirpStack receives and decodes the sensor data. Node-RED then prepares the records for storage and verification. PostgreSQL stores the actual sensor records off-chain, making them searchable and usable for monitoring. Hyperledger Fabric stores the hash values, which serve as secure proof of the original records. During verification, the system compares the current hash from PostgreSQL with the hash stored in the Hyperledger Fabric. If the hashes match, the record is unchanged. If they do not match, the system can detect possible tampering. Now that we've seen how the prototype was designed, the question is whether the system can actually work from end to end. In other words, can sensor data move successfully from the field, pass through each layer, and reach the verification stage? This leads us to the first validation result, reliability validation. The data traveled from the sensor to the gateway to ChirpStack, Node-RED, PostgreSQL, and Hyperledger Fabric. A total of 500 readings were tested. The prototype achieved a 98% success rate, with 490 successful readings. The failed readings may be due to packet loss, delay, or processing interruption. Overall, the result shows that the prototype can reliably transmit and process Plantation sensor data. The reliability test showed that the data could move through the pipeline with a high success rate. But successful transmission alone is not enough. After the data reaches the system and is stored, we also need to know whether it can still be traced and verified. This brings us to the second validation, traceability validation. Here, the goal was to check whether stored PostgreSQL records still match their blockchain hashes. A total of 490 sensor records were verified. All recomputed hashes match the hashes stored in Hyperledger Fabric. This means that the records remain unchanged during normal verification. The system also successfully committed records in batches of 10, 25, 50, and 100. This result shows that the prototype can trace and verify stored sensor records before they are used for farm decisions. The traceability results showed that stored records match their corresponding blockchain hashes during normal verification. But the real test is what happens when the stored records are changed. If someone modifies the data after storage, can the system detect it? This leads to the third validation, security validation through tamper detection. First, 50 original PostgreSQL records were checked, and all match their on-chain hashes. Then, the same records were manually modified and rehashed. After modification, all 50 records produced hash mismatches. This means the system was able to detect that stored records had been changed. In simple terms, if someone alters the data after storage, the prototype can flag it through a blockchain hash mismatch. Taken together, the three validations show that the system can transmit data reliably, verify stored records, and detect post-storage changes. With these findings, we can now summarize the main contribution of the study and discuss the next steps for improving the prototype. This study showed that LoRaWAN sensor data can be transmitted, stored, hashed, and verified using a Hyperledger Fabric-based prototype. The results confirm three key findings: reliable data flow, successful hash verification, and effective tamper detection. The prototype provides an initial model for secure and traceable smart banana plantation monitoring. This is important because farm decisions such as disease risk response, irrigation, and nutrient management depend on trustworthy sensor data. Overall, the prototype offers a secure and verifiable foundation for smart banana farm monitoring. Moving forward, the future work should also include longer field deployment, more sensors, more plantation sites, better dashboards, disease risk alerts, and broader security testing. In conclusion, this prototype offers a secure and verifiable foundation for smart banana farm monitoring. It is still an early prototype, but it shows a practical direction for making plantation sensor data more trustworthy. With that, I now end my presentation. Thank you very much for your time and attention. I hope this presentation has shown how LoRaWAN, off-chain storage, and Hyperledger Fabric can work together to support secure and traceable smart banana plantation monitoring. Thank you once again, and good day.